So our next speaker is Anna Kalogirou from University of Nottingham, and the title of her talk is Evaporation and Deposition of Colloidal Droplets on an Inclined Substrate. Please, Anna.
Thank you very much for the introduction and for the invitation to this very nice workshop. This is some recent work in collaboration with Alexandros Askounis from University of Wolverhampton, who's mainly in charge of the experimental part of this work, and Mark Blythe from UEA. The problem of evaporating droplets that contain nanoparticles is relevant in a variety of applications, but the key application that we had in mind before starting this work is applications relating to photovoltaic systems. So in solar farms, normally the photovoltaic panels are positioned in a tilted position so that they increase efficiency, they can collect more solar energy, and depending on weather conditions, when it rains, droplets will deposit on the solar panels. These will often contain dust, so when they later evaporate, they will result in certain deposition patterns due to this contamination, which may lead to decreased efficiency of these panels. We're interested in understanding these patterns and how they form. Other applications of this problem include biomedical applications, electronics, and coding flows. So the problem of droplet evaporation of just pure liquid has received a lot of attention. A lot of researchers have looked at extensively in this problem, with particular emphasis in understanding the evaporation mechanism and the process and how and what phenomena emerge in the process. For example, droplet spreading, retraction, and pinning of the contact line. I'm mentioning here some key references, and in particular the recent review by Stephen Wilson published in 2023. And also a lot of attention has received the problem of evaporating droplets with particles, because this leads to pinned steps or terraces, and the well-known coffee ring effect. A lot of people in this room have worked on this, and we've seen a number of presentations already this week. But in our work, we're interested in droplets on inclined substrates. This is something that has not received a lot of attention so far, but in nature or around us, droplets are not always on horizontal substrates. In these cases, the droplet is no longer symmetric, and there's a need to understand how the evaporation mechanism changes in this case. So there has been some experimental work so far, mainly listed in these papers, but not a lot of theoretical work. So in recent laboratory experiments done by Askounis and collaborators, they have noticed that they can use these substrate inclination angle to control the deposition patterns of particles. For example, in these pictures, they show some terraces that are formed at the front and at the rear of these inclined droplets. But while I will not focus on experimental work on this presentation, Alex will be here tomorrow, and I think he will present on this relevant problem. But we will use these experimental results to guide our theoretical work. So in this talk, I will present a mathematical model which is derived to include all the relevant physical effects that are important in this problem, including capillarity, Marangoni stresses, evaporation effects, and particle deposition. We will derive the model using lubrication theory, essentially assuming that droplet is slender, and this allows us to reduce the dynamics in a reduced set of PDEs that can be more easily solvable. and I will present results for various inclination angles. So the overall aim is to improve the understanding on the different processes and the evaporation that takes place, and in particular the role of the inclination of the substrate on the formation of these deposition patterns and terraces. So this is the setup of the problem. We have a droplet sitting on an inclined substrate. There's an angle theta with the horizontal, and the droplet has properties, has a constant density. The viscosity mu will be dependent on the concentration of the particles, and the surface tension is also dynamic, namely it depends on the temperature variations. So we will denote by y equals h of xt the position of the interface. And as already mentioned, key physical processes that take place in this problem is that there's evaporation taking place due to the vapor pressures going out of equilibrium. This temperature the evaporation leads to variations of temperature, which also leads to dynamic surface tension. We also have, as mentioned, a reduction of fluid viscosity in regions where there's higher concentration of particles. It was observed in experiments that particles create these terraces, and I will show some results later. And also, a key process at the interface is that usually it spreads at initial times, at early times in the process, and then later the evaporation takes on and droplet retract and eventually disappears. The mathematical model we will consider consists of a number of governing equations. For the fluid flow, we have classical equations, but we will use the lubrication theory, as already mentioned. So essentially, we have Stokes equations. Here in these equations, we have the viscosity, which depends on phi. Phi is the volume fraction, which is a function of the particle's concentration. I will show later the expression for this. We have the effect of gravity, and theta, again, is the inclination angle with the substrate. So these equations come with a number of boundary conditions. We have no slip and no penetration at the solid wall. And at the gas-liquid interface, we have tangential and normal stress balance. In the tangential equation, we see gradients of the surface tension, which, as mentioned already, depends on the temperature due to thermal effects. And in the normal stress equation, we have P is the pressure of the liquid and PV is the pressure in vapor. And on the right-hand side, we have Young-Laplace equation for the surface tension and curvature, and we have a capital Pi is the disjoining pressure. So in addition, we have the well-known kinematic equation that describes the evolution of the interface, where J here is the evaporative flux and rho is the density of the liquid. For the particle concentration, we consider a convection diffusion equation. So particles can be convected with the flow, but they have this diffusion coefficient delta, and there is no flux at the solid boundary, and a diffusive flux is considered at the gas-liquid interface, following these equations. Now, this is mainly the set of governing equations, but there's a lot of unknowns still in here. One of these is the viscosity. I mentioned that this depends on the particle concentration, and it follows a well-known relationship where here mu naught is the viscosity of just a clean fluid with no particles. Phi is the volume fraction. Phi m is the maximum packing fraction. And this volume fraction basically is defined as the total volume of particles divided by the total volume overall of fluid and particles. We also have a dynamic surface tension. Sigma follows a linear relationship proportional to the temperature. Sigma naught here is the surface tension of just a pure liquid. capital T is the temperature, Ts is the equilibrium saturation temperature in the vapor, and gamma is just a sensitivity parameter. So the temperature itself follows its own energy equation. It's a more complicated equation than this, but under the lubrication assumption, it reduces to this simple PD, which comes with two boundary conditions. At the solid wall, we assume that we have a given temperature, Tw, and at the gas-liquid interface, we have a condition that relates temperature gradients to the evaporative flux, where here these constants are lambda is a thermal conductivity and HLB is the latent heat of vaporization. So these are constants that normally we know from experiments based on the problem. And finally, the evaporative flux, we impose a kinetic model for this that basically relates J to the temperature at the interface, which is given by this Ti parameter, and involves all these other constants, which include properties of the vapor, like density, pressure in the vapor, and the saturation temperature. The one missing component that I didn't mention anything yet is the disjoining pressure, which is actually an important factor in this model. So disjoining pressure in this model includes two components. The first one is denoted by pi VW. It's essentially a term that includes, it's due to van der Waals interactions between the particles. And we also include a second component, which is an oscillatory disjoining pressure, which takes this form. Essentially, this is a term that depends on, depending on the particle concentration, we get this oscillatory component, which, if we plot it, it has this form. As h is much larger than the particle diameter, then this whole term just tends to 0. But when we are in regions where the interface is similar to the diameter of particles, then this component becomes important. And it's the term that is responsible for the terrace formation in the flow. There's a number of functions here. All these F1, F2, and F3 are all functions of volume fraction, but they're all positive. However, sorry, a point here. The term F1, which appears in the argument of the cosine, is responsible for these terraces, because when you have a higher concentration of particles, which normally happens near the contact line, then you have an increase in this function F1, and then the argument of the cosine changes sign, which leads to this oscillatory component and eventually the creation of terraces. So, as mentioned already, we will consider slender droplets, so the aspect ratio will be assumed small, and we non-dimensionalize the problem, which leads to a number of non-dimensional parameters. This is just some of the dimensionless groups we have in the problem. The capillary number is taken to be equal to epsilon cubed, where epsilon is the aspect ratio, and this can be done by choosing appropriately the velocity scale. We have the bond number, which is important here because it allows us to control the effect of gravity due to the inclination angle, and a number of other parameters that are related to either the presence of particles, diffusion, or temperature in the problem. So we can then go back to our governing equations, and we can slowly start solving one by one to obtain the lubrication equation. We start with the particle concentration, and here it's a well-known assumption when you have a lubrication flow, like a thin film. You assume a rapid vertical diffusion of the particles. Essentially, the assumption is that epsilon squared times the Peckel number is very small, and this allows us to expand the concentration of particles in this form, where the leading order term is independent of the vertical variation. So the first term, it's only a function of x and t. And substituting this expansion into the convection diffusion equation gives rise to a simplified PDE with some boundary conditions that can be solved together to give us a PDE which is only for the leading order concentration C0. So here we have U bar is the average velocity, horizontal velocity in the fluid defined by the integral of U. We also have the evaporative flux. Both of these terms will be obtained later in a couple of slides. And if we look at the dimensionless momentum equations, we have the horizontal and vertical momentum, where now the viscosity, which is a function of the volume fraction, depends on this phi naught, which is a leading order volume fraction depending on the leading order particle concentration, C naught, and defined this way. And if we want to retain gravity effects in the leading order, looking at this term, we rescale the bond number to be proportional to epsilon, but this makes the second equation become equal to 0 on the right-hand side at leading order, and this allows us to just integrate and obtain expression for the pressure using the normal stress equation. Here we have the disjoining pressure again, which in non-dimensional terms, it has the two components, as already explained before, where the oscillatory component now only depends on the leading order concentration of particles. Right. So we then need to solve for the temperature equation. It's a simple PDE that can be integrated, and using the two boundary conditions, we just find a linear relationship for the temperature that involves the evaporative flux, and this can now be used in the constitutive equation that connects the evaporative flux with the interfacial temperature and takes this form. So basically, Ti here is the temperature at the interface, which can be obtained by this expression. Eventually, combining these two together, we find an expression for the evaporative flux that depends on H only, and it involves the disjoining pressure, which, recall, it's a function of the particle concentration. A remark at this point is that there are regions in the flow where, if we find regions where the evaporative flux is 0, this gives rise to an explicit expression for the interfacial height, which is constant, and it's an expression related to the system parameters, and this is the precursor film thickness, which is basically the thin film that exists in regions outside the droplet, and it's where there's no evaporation. So finally, going back into the horizontal momentum equation, we can then, having found the pressure expression, we can solve this to find the leading order horizontal velocity, where we've used the surface tension. It's approximately 1 at leading order in epsilon. This can be integrated to find the cross-sectional average, is U bar, which is needed in the leading order particle concentration equation, and also in the evolution equation for the film for the thickness of the interface, which is given here. So in summary, we end up with two PDEs, coupled PDEs for H, which is the thickness of the fluid, the liquid, and C0, which is the leading order concentration of particles. These two PDEs are coupled, and they involve the cross-average velocity, the pressure, and the evaporative flux. But all these, we have found expressions for these in terms of H and C0. So this is a closed system for these two variables. So we will solve the PDEs using finite difference method, and we will only simulate for half of the droplet, basically from the tip of the droplet at x equals 0 up to some far field value x equals L, where we can apply appropriate symmetry conditions. The initial condition will be like an inverse parabola, which is basically like a spherical cup droplet with uniform concentration everywhere. So we assume that the droplet has a given height and a given radius initially. The biggest challenge in this problem is that, well, if you have a horizontal substrate, your droplet is symmetric, so you can just take half of it, simulate this half, and just mirror the other half would be exactly the same. But here, because we have an inclined substrate, the droplet is asymmetric, and it has a different contact angle in the advancing part and in the receding part. So the question is, how do we find where the tip of the droplet would be to simulate these two halves? So here we've used some experimental data for contact angles to find the theoretical contact angle we need to use in the model. The two are connected using this relationship where basically the tilde angles are the experimental ones, and here we have the capillary number, and the non-tilde theta c, it's the theoretical contact angle. So we can fix the capillary number, and experimentally it was contact angle was measured about 30 degrees. So this gives rise to a theoretical value of 76 degrees. This would correspond to a droplet on a flat substrate. So this would be the contact angle we need to use for the dimensionless theoretical model as the initial condition. Question is, what should be the contact angles for the advancing and the receding parts? Again, we used experimental data from this paper to find a relationship that connects the contact angle of a flat droplet and how this changes when you incline the substrate. And then we extended this expression, this relationship for the theoretical model. Eventually, we used this table, so this will be the parameters used in the numerics. So we have 4 inclination angles, like a flat substrate, and 10, 20, and 40 degrees. For each one of these, we have used certain advancing and receding contact angles initially, and the radius changes appropriately so that the volume of this of the half droplet is the same in each case. And then we fix the height to be the same so that we can then connect the two halves at the tip. Okay, so these are some numerical results for a flat droplet for now. So theta equals 0, so there's no inclination. The different curves in this top left panel show different time snapshots of the evolution of the droplet. Initially, the droplet is at height 2 and ends at x equals 1. But then we notice that at the very early times, it spreads a bit, and then later it starts retracting due to evaporation, and volume decreases until eventually the droplet disappears. This is the evaporative flux at the same times. We see that it achieves a peak value at the edge of the droplet where the contact line is, and then decreases towards the bulk. Now, if we take this plot and zoom in towards the region near the bottom, we see these terraces which are formed because the particles tend to gather near the contact line, and then when there's no more space, then they form layers of particles, eventually forming these terraces. This final plot shows the concentration of particles, and it confirms that indeed, in each case, we have peaks in the concentrations near where the terraces are formed. So next, we extend these results to other inclination angles. So these are the initial conditions we've used in each case. Basically, the droplet is now asymmetric, and we use initial condition using the contact angles that I explained earlier in each case. And these are just the final results. Now we're only showing the terraces that we get. The first one is for no inclination, so it's symmetric on both sides, while in all the other plots, the part on the left is the advancing part of the droplet, so where gravity acts, and the part on the right is the receding. So essentially the key result here is that as you increase inclination angle, you see longer terraces in the advancing part. Eventually, for the largest inclination angle, you see these much longer terraces are formed at the advancing part of the droplet compared to the receding part. Yeah, so this is pretty much it. Summary is that we've looked at evaporation and deposition of colloidal droplets on inclined substrates. We derived an appropriate lubrication type model for sessile droplets. The key component in this model is structural oscillatory disjoining pressure, which is responsible for the formation of terraces. And we investigated the effect of gravity on evaporation and deposition. These are just some preliminary results, and they seem to agree with experimental observations, even though I didn't show any experimental observations. We do aim to perform a more qualitative comparison in the near future, and I hope Alex tomorrow will be able to show some numerical, some experimental results on the same problem. Thank you very much.
Thank you very much, Anna. Questions?
Maybe that's a stupid question, but you are in 2D, 2D axial symmetry, because I don't understand what will be the shape of the droplet with a receding contact angle and advancing contact angle in 3D, because you know you have the receding contact angle at the top and the advancing at the bottom, but how does it connect together, and did you think about that a little bit?
We haven't thought of 3D, but would be a good
That was just a question. Maybe a second question is what's the role of the disjoining pressure, like oscillating disjoining pressure, on the evaporation flux, I would say. I would say the dynamics of the receding of the droplet. If you don't put these ingredients, is it evaporating faster, slower, and this kind of thing?
If you don't put the oscillatory...
Yeah, exactly.
I think the evaporation is not as much affected by the oscillatory pressure. It's mostly the presence of these terraces that emerge when you add this component. The evaporation is mostly dependent on the temperature effects and the spreading and the receding of the droplet itself, which is still going to happen without the oscillatory disjoining pressure.
The solution that you obtain is moving at constant speed, or is it fixed?
I didn't check the speed of the...
Because that could be, to compare with experiments, that would be a nice, a nice correlation.
So at first, the time it takes to spread, it's much shorter than the time it takes to then slowly evaporate. So, but it's... I will
look at somehow to get the law between the contact angles and the velocity to somehow to obtain.
Okay, thank you very much, Anna.